physicists were generally filled with excitement as they observed the long-awaited activation of the most advanced high-energy particle collider. After persistently waiting for many years, they had finally witnessed this significant innovation poised to transform our understanding of the universe. The Large Hadron Collider, constructed by the European Organization for Nuclear Research, became operational in September 2008 following a carefully extended development phase. Nevertheless, it took the machine designers a considerable amount of time to complete it. Since then, the Large Hadron Collider has played a crucial role in solving various cosmic mysteries during its numerous experimental runs. However, recent advancements have raised concerns among researchers at CERN. After ramping up the collider to a new peak energy level, they detected something unexpected and alarming. Subsequent investigations have led to various theories attempting to explain this anomaly, but they remain unconfirmed and speculative. The universe is full of unexplained mysteries, and over the years, scientists have dedicated their efforts to exploring and understanding some of them. These mysteries include the vast black holes observed in space, which are said to have such a strong gravitational pull that even light cannot escape. Additionally, there is the enigma of what lies beneath the Bermuda Triangle, also known as the Devil's Triangle, infamous for the mysterious disappearances of over 50 ships and 20 airplanes. However, these mysteries remain unexplained due to the limitations of technology. In the mid-20th century, physicists sought better methods to investigate the fundamental building blocks of matter. In 1932, physicists John Douglas Cockcroft and Ernest Walton created the first functional particle accelerator. These accelerators are crucial for studying the fundamental components of matter by accelerating particles to high energies and colliding them. Through these collisions, researchers can observe the interactions and test the fundamental forces and particles that constitute the universe. Given the importance of particle accelerators in unraveling cosmic secrets, CERN constructed the world's largest particle accelerator. However, researchers have recently discovered that this atom smasher could potentially cause the Mandela effect due to its ability to alter the fabric of space and time. The Mandela effect refers to the phenomenon where people remember events differently from how they actually occurred. This term was coined in 2009 by Fiona Broome, who discovered that she and many others mistakenly believed Nelson Mandela had died in the 1980s, although he passed away in 2013. Several factors can contribute to this effect, such as false memories and the powerful influence of social media and the internet. Nonetheless, some researchers have raised concerns that past upgrades to the LHC might have also induced the Mandela effect. Before dismissing this concern as paranoia, it is worth noting that prominent scientists and other notable figures have expressed their worries. Stephen Hawking was among the first to voice his concerns about the impact of the Large Hadron Collider, warning in an interview that the collider could create black holes that might threaten the universe. Another researcher, Dr. Carlo Rovelli, shared his concerns about the LHC in a blog post, suggesting that it might produce exotic speculative particles that could alter surrounding matter. Even public figures have commented on the potential risks associated with the Large Hadron Collider. Astrophysicist Carl Sagan and science fiction author Arthur C. Clarke also expressed concerns about the collider, proposing that it might create strangelets or even a black hole that could swallow the Earth. During a press conference, President Obama also voiced concerns about the collider causing a catastrophic event that could affect reality. The fact that various groups of prominent individuals, from scientists to scholars and celebrities, have expressed unease about the LHC underscores the seriousness of these concerns. While the outcomes cannot be predicted with certainty, it is essential to carefully consider the potential risks and make informed decisions about operating the collider. So, can CERN's LHC cause the Mandela effect and other changes in our universe? The Large Hadron Collider is currently the largest and most powerful particle accelerator in the world. It was built between 1998 and 2008 with the collaboration of over 10,000 scientists from more than 100 countries. It became operational on September 10, 2008, and is the most recent addition to CERN's accelerator complex. The goal of this atom smasher is for physicists to test predictions of various particle theories, including measuring the properties of the Higgs boson, searching for the vast array of new particles predicted by supersymmetric theories, and investigating other unresolved questions in particle physics. The collider consists of a 27 kilometers ring that is surrounded by strong magnets, which accelerate particles to high speeds and energies. Within the accelerator, two beams of particles are accelerated almost to the speed of light before being directed to collide. These beams travel in opposite directions through separate tubes called beam pipes, which are maintained at a very low pressure. The beams then follow a circular path around the accelerator due to a strong magnetic field generated by the magnets. Lead ions are the preferred choice for this program, and they are accelerated to an energy of 2.3 TeV per nucleon or 522 TeV within the LHC ring. The LHC operates with a vast amount of energy and generates massive data collection, highlighting the scale and significance of this scientific endeavor. The CERN site consumes roughly 200 megawatts of electrical power from the French grid during LHC operations, which is about 1/8 of the energy usage of the city of Geneva. Notably, the LHC and its detectors contribute around 120 megawatts to this demand, surpassing the energy achieved by previous relativistic heavy ion colliders. The heavy ion program aims to investigate quark-gluon plasma, a state of matter believed to have existed shortly after the Big Bang, providing insights into the fundamental nature of matter and the universe. With the help of this particle accelerator, one of the major theories in particle physics regarding the existence of the Higgs boson particle has been confirmed. The Higgs boson, often referred to as the God particle, was detected at CERN in 2012, marking a significant breakthrough in the field of particle physics. If you're wondering how the Higgs boson earned its nickname, it comes from a book titled The God Particle by Leon Lederman published in 1993. However, this nickname has faced criticism from many physicists for potentially misleading the public about what the particle represents. The Higgs boson is a subatomic particle in the standard model of particle physics, arising from the excitation of the Higgs field. In the standard model, the Higgs particle is a massive scalar particle with zero spin, no electric charge, and no color charge. It is associated with mass, and the particle is highly unstable, decaying into other particles almost immediately upon its creation. The Higgs field, which resembles a Mexican hat, is an invisible energy field with both electrically charged and neutral components. This field influences how particles interact, providing mass through what is known as the Higgs mechanism. The Higgs boson and its field are named after Peter Higgs, who, along with 5 other researchers, proposed the particle's existence in 1964. After extensive searching, scientists finally detected a particle with the predicted properties of the Higgs boson in the LHC. Finding the Higgs boson as expected was crucial because the particle helps explain why some particles have mass, an essential property that affects how things behave and interact. It also helps elucidate how things in the universe interact with one another and form the fundamental building blocks of matter. To create Higgs bosons, researchers collide 2 high-energy particle beams at extremely high speeds. Occasionally, a Higgs boson is produced in such a collision, but it decays rapidly, making it difficult to observe directly. Instead, scientists examine the byproducts of the decay and determine if the observed decay pattern matches predictions for the Higgs boson. If the pattern is consistent, it suggests that a Higgs boson was indeed created. However, creating a Higgs boson in a collision is rare, and many other types of collisions can produce similar results, so scientists must analyze data from trillions of collisions to be certain. They need to identify the same pattern across different detectors and ensure it is not just a random background event. Extensive scientific research has been conducted to explore potential connections between the Higgs field and the Big Bang, a speculative field proposed to explain the rapid expansion of space during the universe's early moments, known as the inflationary era. Some theories suggest that a major field, such as the Higgs field, might be responsible for this phenomenon. The fate and nature of our universe have become subjects of investigation because, according to the standard model, the universe's vacuum state could remain stable for an extended period, but it is not particularly stable. This means that the universe might become more stable in the future, potentially altering everything we currently understand about it. The stability of the vacuum that contains the universe depends on the properties of the Higgs boson and top quark, and if the universe is in an unstable vacuum, it could lead to massive changes in the distant future. There is a need to accurately measure the mass of the top quark using a specialized collider known as an electron-positron collider to understand what might ultimately happen to the universe if the vacuum stability changes in the future. Researchers also believe that the Higgs field is the energy filling the vacuum, influencing the extreme energies of the universe's early moments. This idea suggests that the Higgs field has undergone several changes over time, creating the forces observed in the universe. Scientists are currently investigating the Higgs field's connection to the energy present in empty space. The energy observed in space today is close to nothing, yet theories involving the Higgs field suggest it should be much higher. This discrepancy presents a significant problem in physics known as the cosmological constant problem. Looking back at history, we can see how particle physics has advanced our understanding of the fundamental building blocks of matter and forces. In the 1960s, scientists faced challenges trying to unify the electromagnetic and weak nuclear forces using quantum field models. The theories of that time, such as the Yang-Mills theory, predicted that certain particles we knew had mass should actually be massless, creating a major issue. Additionally, the Goldstone boson theory proposed the existence of massless particles called Goldstone bosons, adding to the difficulties. Initially, researchers did not focus on this theory, but it eventually became significant after significant progress was made by theorists such as Martin Veltman and Gerard T. Hooft. These advances helped to resolve several issues within particle physics and contributed to the development of the Standard Model. The integration of different forces and particles into a unified theory required overcoming numerous theoretical and experimental challenges. The detection of the Higgs boson was a pivotal moment in this journey, confirming the existence of a fundamental particle that provides mass to other particles, thereby solidifying our understanding of how the universe operates on the smallest scales. The Standard Model itself, however, is not the final theory of everything. It successfully describes the electromagnetic, weak, and strong nuclear forces but does not incorporate gravity or explain some of the universe's most profound mysteries, such as dark matter and dark energy. The discovery of the Higgs boson has been a crucial step, but it also highlights gaps and questions that remain unanswered. For example, while the Higgs mechanism explains how particles acquire mass, it does not fully account for the observed discrepancy in the cosmological constant, which is a measure of the vacuum energy of space. Furthermore, the search for a unified theory that can incorporate all fundamental forces, including gravity, continues. Theories such as supersymmetry and string theory offer potential pathways beyond the Standard Model, but they remain speculative and require further experimental validation. The Large Hadron Collider plays a key role in exploring these possibilities, as its high-energy collisions provide the means to probe deeper into the fundamental structure of matter and the forces that govern it. In conclusion, while the Large Hadron Collider and the discovery of the Higgs boson represent significant milestones in the field of particle physics, they also open new avenues for exploration and inquiry. The ongoing research at CERN and other particle physics laboratories around the world aims to address the remaining questions and to further our understanding of the universe's fundamental nature. As science progresses, we can expect new discoveries that may reshape our comprehension of the cosmos and the underlying principles that govern its behavior.